Hello. In this video we're going to do the very last chapter, chapter 15, and it's about the estimation of dynamic causal effects. So let me start with a little bit of an overview about what we're trying to do here, what these dynamic causal effects are. So let's just think about a two-variable model where we have x on this axis and y on this axis. And y is just moving along at its mean, at its normal value. So y is going along here at y bar. And suddenly at some point, time t, there's a shock to the variable x. What we want to do is trace out, maybe it goes up, what happens at time t, t plus 1, t plus 2, and so on. And so we can use these, as we'll see there, it's a distributed lag model. We can use these models to estimate what these effects might look like. So one possible pattern is that it jumps up and then it slowly returns to the mean over time. If the variable's stationary, it will in fact, if there's just a single shock and then the shock goes away, and that's the only thing that happens to x, then this will in fact go back to the mean value if it's stationary. But we just want to look at these patterns. It could go down. It doesn't have to be smooth like this. It could first go down and then up and have all sorts of, well, that's kind of the same. It could have different sorts of patterns than this one, depending upon the model that we're looking at. And we want to look at this. For instance, this might be the federal funds rate, and this might be GDP. And we might want to know, well, what's the effect of a shock to the federal funds rate, like the Fed would do, on output, on Y. And so that's what we're going to be looking at. Now, the basic model we'll be using is fairly simple. It's simply yt equals beta naught plus beta 1 xt plus beta 2 xt minus 1 out to beta p plus 1 x t minus p plus some error ut, like always. And we'll be able to use this model to estimate those dynamic causal effects, as we'll see in a moment. Okay, so that's the basic model. Now, what we're going to have in this chapter, and this is also true of the empirical assignment, is there will be two basic cases. So we're going to distinguish between two types of exogeneity, and I'll do that in a little bit. I just want to sort of outline where we're headed so you have the bigger picture. This model can be estimated in different ways depending upon the type of exogeneity that we have. And so we'll look at a case where we just have regular old exogeneity, just we'll call it exogeneity. And another case, and again, I'll define these later, of strict exogeneity. Now in this first case, we can use OLS with robust errors to take care of any serial correlation or perhaps heteroscedasticity, but mostly serial correlation in the error terms. We'll come to that in a few minutes. So we have just exogeneity. It's fairly simple. It's just the OLS we've always done with the robust standard errors, and you've got it. When you have strict exogeneity, one way is to do OLS, but the form of the model that you need for OLS is not one that's really convenient to deliver the coefficient estimates. I'll be more precise about that later. And the other way will be a new estimation technique we use called GLS. So this is really the only new estimation technique in the chapters, is what the heck is this GLS? The rest is just, from an estimation point of view, things we've done before. In this case, you have to get the model in the right form. And we're also trying to learn how to interpret the kinds of questions these models can answer, the way they can give us these dynamic causal effects. Okay. Just to give an example, one thing first. So let's talk a little bit about causal effects. and time series data. So that's one of the sections in the text. And the point we want to make here is that earlier we've defined causal effects to the outcome of a idealized random controlled experiment. So before, let me just write that down since I didn't say it as clearly as I had hoped. We defined causal effects as the outcome of an idealized randomized controlled trial. So we use examples like you'd apply fertilizer randomly to plots of land, use genetic cones to control for genetic effects, randomize the treatment across the plant. Some are treated, some aren't. You do that randomly in case there's any differences in the soil across the plants or other conditions. It'll cancel out, and so it saves you for having controls. Though if you can include controls like the soil type or something like that, that would improve the efficiency. But you don't have to get consistent estimates and so on. And so we had multiple subjects, a group of people, a group of plants, something like that, a group of schools, a group of classes, whatever our subjects are that we're going to treat somehow. Maybe class students are treated with different numbers of different class sizes like we looked at earlier or something like that. And it's usually cross-section data or panel data when you do these RCTs, randomized control trials. And you have more than one individual. So it's possible, because you have multiple subjects, it's possible to have treatment and control groups. So we take this random sample from the population. From that random sample, we randomize the treatment, and then we're all set to go with this kind of a setup. The problem in time series data is that you don't have multiple subjects. Suppose you want to estimate, say, the effect of a change in the federal funds rate on GDP today and over time. So you change the federal funds rates today. How does GDP respond dynamically over time? Well, in that case, we only have one subject, the US. Now, you might be able to take a cross-section of countries, say a bunch of different developed countries, use those as your cross-section and turn it into a panel, and use some of those techniques. But generally, the institutional structures across countries are so different that the all else equal assumption that you need, and you don't have enough to really randomize if you only have, say, 10 countries. And so you really can't get the equivalent of a randomized controlled trial out of that for those reasons. And often you're just interested in the outcome for one country anyway. So if you only have one subject, what could you do? Well, you could certainly imagine an individual person being subjected to individual treatments or no treatments over time. Maybe some days you give them the treatment, and the other days you give them a placebo, and they can't tell the difference, and you observe their blood pressure or something like that. So you could imagine doing a randomized control trial on an individual. And that's really what we want to think of with time series as we think of causal effects and what it means to have these RCTs. So for time series, think of an RCT, randomized control trial, as the same subject for example, the US economy, being subjected to different treatments over time. So for instance, with the federal funds rate, we can think of a case where sometimes there's no change in the federal funds rate, sometimes there is, sometimes it's a big change, sometimes it's a small change, depending on what the Fed is doing. And so we can use those periods of no change as controls against the periods where there is change as the treatment, and get sort of the equivalent notion of a randomized controlled trial. And then we can talk about the assumptions that you would need to get actual causal effects out of an experiment of that type. And that's basically the way we're going to think about this. Okay. So let's do a quick example here. I want to pull something else out here just a second here. Let's do a quick example of how these models work so you can get a notion of what these multipliers, how to calculate these multipliers. So suppose you want to, and this is actually the question in your empirical assignment, suppose you want to estimate output yt is beta 0 plus the federal funds rate ff at t, oops, I forgot my beta 1, plus beta 1 FFT plus beta 2 FFT minus 1 all the way out to beta P plus 1 FF T minus P plus UT. Now what we're going to do is we're going to keep the federal funds rate constant. So we're going to imagine the federal funds rate is, let's just make it 0 in every period except 1. It really wouldn't matter what we made it. We would have to renormalize around whatever mean. So it's easiest to just think of the federal funds rate as being 0 in all periods. And here we're going to have a shock of 1 unit. That is, the change in the federal funds rate at t is going to be 1. So it'll be 0 here, 0 here, 0 at t minus 2 and 3 and so on, 0 every place else, and it's 1.0 here. Or it's whatever the constant value was, plus 0 and plus 1. Maybe the federal funds rate we just want to have it at 3%. This would be 4, and those others would be 3. Then you could just normalize the mean around that. But it's easier to think of it this way. Okay. So the change in yt would be equal to what? Well, it would be beta 1. When the federal funds rate changed, so for a change in FFT equal to 1 and all other changes are 0, the change in yt would be beta 1. What would the change in yt plus 1 be? Well, think of what the model would be in that case. You would have yt plus 1 equals beta naught plus beta 1 ff t plus 1 plus beta 2 fft plus beta 3 fft minus 1, and so on until you get to the error term. Now, the only one that changed is FFT. So this is 1.0, this is 0, this is 0. All the other ones are 0. We're just looking at a change at a point in time of 1 unit. And so the change in yt plus 1 would be beta 2. So what do you think the change in y t plus 2 will be? If you guess beta 3, you'll be right. Because if I change this to t plus 2, this would be t plus 2, this would be t plus 1, this would just be t. And so this coefficient, now this would be 1.0, and this would be 0. Now this coefficient would be the change. And so you can take that all the way out to the change in y t plus p would be beta t plus p. After that, all the changes are 0. The change, I'm not sure if that'll stay on the board. The change in y t plus p plus 1 equals 0, and that's true from then on. Because once I get past t minus p lags, FFT will be gone. The first term here would be FFT plus 1, and then t plus p plus 1, then t plus p, and you wouldn't get to ft once you got past p. So once you get to t plus p, that's the last one, right? What would y t plus p plus 1 be? That would be beta naught plus f beta 1 ff t plus p plus 1 plus beta 2 ff t plus p plus this one's t minus whatever. This is just p back. So this is going to be beta p plus 1 times ff t plus 1 plus ut. We'll be past, the very last term will be ft plus 1. For t plus p, this would be ff at t, and you'd get beta p, this should be t plus p. So one period back, when this is just t plus p, this would be fft, and you'd get this coefficient for the multiplier. But here it's going to be 0. So there'll be 0 past t plus p. Okay? Hope you've got that. So there's some names for these different multipliers. So the impact multiplier that's just beta 1. That's the effect of the shock to xt at time t. So it's just this coefficient here. Then you get what are called beta 2 up to beta p plus 1. These are all called interim multipliers. They give you the effect. This is the effect after 1 period, beta 2. This would be the effect after p periods. After p plus 1 periods, it's gone, it's 0. But this gives you the effect. And so if you add all these up, beta 1 plus beta 2 plus beta 3 out to beta p plus 1, that is called the cumulative. Sometimes it's called the long run. And sometimes it's called the total. Those are all the same multiplier. So it's called the cumulative multiplier, the long run multiplier, the total multiplier. It's the total effect of the shock. So this is the effect in this period, the effect in this period, and the next period, and so on. If I want to know the total effect on y, I have to add them all up. And so this is the total impact. How much y changes overall. Yeah. All right. Make sure I didn't want to say anything else there. The other thing you can do is you can graph these. So if I want to know how y changes after a shock, I can just graph these coefficients. And so at time t, the effect would be beta 1. At t plus 1, the effect would be beta 2, and so on. T plus 2, the effect is beta 3. And then you can just plot what this looks like over time, where this is y bar. The way you get y bar, the way you actually do this, I guess I should say it, you start off at y bar by putting ff and its lags at ff bar. So you just put it at the average over time. So this is where y usually is at. Then you deviate FFT from the average by 1 for just that one time period. And then you see what happens over time. And so this is the deviation from the mean. And you could work out that algebra too. This is just more intuitive to think of these being 0, but it doesn't really matter. OK, but anyway, you can plot these over time, and that gives you a picture of the dynamic effect. So in this case, it takes a while for y. It takes a period for y to reach its peak. So there's a delay of a quarter if this is quarterly data, a year if it's yearly data, whatever. And then it returns back to its initial value over time. So the effect of the shock is not permanent. And that always happens when you have stationarity. OK, now let's turn to what determines which estimation technique we'll use for this model. And that is these two different types of exogeneity. So the first type is just, it's really what we've already looked at. It's what makes OLS work. And so regular old exogeneity, so we need exogeneity for the coefficients as always to be unbiased and consistent, or at least consistent, and so on. But there's two types of exogeneity that can happen. So the first type is just that the expected value of ut given xt, xt minus 1, xt minus 2, and so on equals 0. So this is always often called past. Past is t minus 1 back, and present xt exogeneity. And the general estimation technique for this first case is going to be OLS with robust standard errors in general. If you can argue you have no serial correlation or heteroscedasticity, yeah, just use OLS. But in generally here, you'll want to use the HAC errors to correct for any potential problems with autocorrelation. The other type of exogeneity is strict. So this one is just exogeneity. The other one is strict exogeneity. And what this says is the expected value of ut given future values of xt, back to say t plus 2, t plus 1, xt, xt minus 1, and so on is 0. So this is past, present, and future exogeneity. So here, ut just has to be independent of the past, of the present and past values of x. Here, for strict exogeneity, ut has to be unrelated to future value of x, the present value of x, and past values of x. So this, for this, and we haven't talked about it yet, well, we've talked about OLS. You'll either use OLS for one form of the model or GLS. And I'd recommend using GLS. That's how I always do it. I haven't actually, ever estimated one of these with OLS except to, as an illustration. All right, so those are the two types of exogeneity. So how can this get violated? This one, the example the book uses for strict exogeneity is they were regressing tomato yield on fertilizer with the fertilizer randomly assigned. And tomato yield today doesn't depend upon fertilizer applied in the future. And so in that case, you would have strict exogeneity. There's no feedback from the, there's no way that future fertilizer or even the expectation of future fertilizer is going to affect yields today. Now with something like the federal funds rate, so say this is the FF rate, it's our model of YT on FFT and lags, what we were looking at earlier, then it's going to be harder to justify this because it may be that the expected future value of the federal funds rate affects the output today. So there's not as much investment, or maybe there's more investment because you know, maybe there's more investment in housing because you expect interest rates to go up in the future or something like that, and that causes GDP to be higher, something like that. And if the expected future federal funds rate is correlated with actual federal funds rate as you think it would be, then you're not going to have this strict exogeneity. In fact, with this example, even though I'm going to have you do it on your empirical assignment, it may even be hard to justify this kind of exogeneity. Because with the Taylor rule, which is where the federal funds rate depends upon output and inflation, if that's a contemporaneous relationship, then it's going to be hard to argue that the current value of output or that the error is independent of xt. But anyway, so these are just things you have to think about and ask yourself which, for the particular problem at hand, you just have to think about the problem and say which type of exogeneity is more reasonable here. Can I justify strict exogeneity? And the reason you would want to is that if you have strict exogeneity and you can use GLS, or this other OLS technique, but let's say GLS, it's more efficient than using this first technique. And so this is a more restrictive condition, and it gives us a more efficient estimator. Now the other thing to note here, let me just leave up the two definitions. If you look at these two, did I have an equals 0 here? If I didn't, there should have been, the whole time, there should have been an equals 0 there. I'm not sure if I erased it or it was never there. Okay, if you look carefully at this, this is strict. It has to be the case that strict exogeneity implies exogeneity. Because if you just forget about this part, this condition is subsumed in this condition. And so if UT is independent of past, present, and future, of course it's also independent of just present and past. It's not true that this implies this, though. So if you have strict, you also have exogeneity, but the reverse is not true. All right, let's go through the assumptions. So now we're going to look at ordinary exogeneity. So let's look at estimation with exogeneity. Not strict. So this is just ordinary exogeneity. So we're assuming that the expected value of UT given xt, xt minus 1, and so on, is 0, just like we just said. Okay, so you can use OLS if the following assumptions are satisfied. So these are the assumptions you need in a time series model to make sure that OLS has desirable properties. So the first condition is one we just talked about, and that's that xt is exogenous, as that condition holds. We've already explained that, so I don't have to say anything there. The second condition is one we ran into in chapter 14. The random variables, RV is random variables, yt and xt have stationary distributions. Comma, and b yt xt and yt minus j xt minus j are uncorrelated as j goes to infinity. Third, that we covered in chapter 14, so there's not much to say there. Large outliers are unlikely. That's the same thing we've always said, but it takes a little bit more restrictive condition in a time series model than we've seen before. So here you need that yt and xt have more than 8 non-zero finite moments. Because of the correlation that you can have in time series models, you need a more restrictive condition. So this is the only thing that's really different so far. So a more restrictive condition for outliers. And the fourth one is there is no perfect multilinearity. Nothing new there. It's just something we have to note as one of our assumptions. So if those are satisfied, so if those conditions are satisfied, the estimators are efficient and consistent. Now, if we want to, we can add more x's. It should be straightforward to see how to do that, so I'll just note it quickly. You just do the same thing. You add more lags of other x's. So something like yt equals beta 0 plus beta 1 xt1 plus beta 2 x t minus 1, 1, where x1 is one of the variables. Maybe you have plus beta 3 xt2 plus beta 4 xt minus 1, 2 plus ut. So this would just be a case where you have two x's, the present and the lag value of x1, present and the lag value of x2. You could add a third, you could add more lags. It should be obvious. What you need here, the most important assumption, is expected, or the one that's most likely violated as well, xt minus 1, 1, and so on, xt2, xt minus 1, 2, and so on. So you just have, and that's equal to 0. You just have present and past exogeneity for both variables, or as many variables as you have. Okay, now let's add a slight wrinkle, which will only result in us. So far, we could just use OLS because all of our assumptions have been satisfied. But what if you had yt equals beta 0 plus beta 1 xt plus beta 2 xt minus 1 plus beta p plus 1 xt minus p plus ut. So what if we have this model and, or where, probably a better way to say it, where ut, see, we use phi1 in this class, yeah, is phi1 times ut minus 1 plus ut bar, where this is white noise. That has all the nice properties, ut bar, but ut is serially correlated because ut depends upon ut minus 1. So that violates one of our assumptions. And so the question is, what do you do in this case? And this could be, it could be more general. You could have, say, ut is phi1 ut minus 1 plus phi, let me call this phi q, because I've already used p here. Normally you use a p for these. ut minus q plus u bar. It could be something like that, too. I'm just using a first order autocorrelation as an example, but it could be pth order, or qth order here, autocorrelation in the error terms. Well, here you'll just use OLS with HAC, robust standard errors. It introduces a lot of theoretical complexity to solve this. But in terms of estimation, it's just, okay, I estimated with OLS with robust errors to take care of the serial correlation. And again, this is all for the case of just ordinary exogeneity. I'm not sure this is really needed. It's not hard to get the dynamic multipliers. But I'm going to talk about it anyway because the book does it. You can use a trick. To estimate the cumulative dynamic multipliers. Earlier, let me just go back and do something earlier. Earlier I said, so suppose our model is the one we're going to use here. Is beta 0 plus beta 1 xt plus beta blah, 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 t plus p plus 1, sorry. Beta p plus 1 x t minus p plus ut. And I mean, if you estimate this and say use HAC errors because you worry about autocorrelation, to get the multipliers, all you'd have to do is just add another line to your code that just says add these up, underscore b bracket x, so on, plus underscore b bracket x t, whatever you called it, lx, l dot x, plus the next beta, l dot 2x, and so on. Just add them up. So in the code, this would be fairly easy to do. So I'm not sure this is really necessary, but the book talks about it, so I'll go ahead and do it anyway. You can estimate the model yt equals delta naught plus delta 1 times the change in xt plus delta 2 times the change in x t minus 1 plus delta r, the change in x t minus r plus 1 plus delta r plus 1 x t minus r, and there is no delta in front of this one. There is on all the others. That's intentional, plus ut. If you estimate it this way, delta naught will equal beta naught, delta 1 will equal beta naught plus beta 1, delta 2 will be beta naught plus beta 1 plus beta 2, and so on. Delta r plus 1 will be the sum up, and delta r plus 1 would be the total cumulative multiplier. These things in here would be what we'd call the interim total multipliers, or the interim. Beta 1 is the interim multiplier, but it's not the cumulative. Beta 2 is the interim multiplier, but it's not the cumulative. So these things here would be the interim cumulative multiplier. Beta 2 itself is the change in y after 2 periods. What this is the total change in y after 2 periods. So this is just the change in that second period. This here adds them all up. So if you were to estimate this model with OLS, or if these happen to be, I didn't mean to put a bar there, or if these happen to be serially correlated, use HAC errors, you could, the cumulative multipliers pop right out of that, if that's what you want. But again, it's really not hard to do with the basic model, so I'm not sure with computers that's really that important to know. If you're doing it by pencil, then that trick is helpful. The HAC standard errors are discussed in a fair amount of detail in section 15.4. Other than knowing you should use them when there's autocorrelation, when you use OLS with just regular exogeneity, that's really all I want to say about the HAC. Okay, now let's move on to case 2, which is strictly when we have strict exogeneity. Now the main estimation method we're going to look at here is GLS. It stands for generalized least squares. And if I could use some matrix algebra, I could show you why that's called generalized least squares, but it's just a different estimation technique. This contains OLS as a special case. That's why it's general. All right. Let me give an example of GLS. So essentially, what GLS does, so you have a model and you have some problem with it, like heteroscedasticity or autocorrelation, and so your assumptions you need for OLS aren't satisfied. What you can often do is find a transformation of that model that gives you the right assumptions back. It gets rid of whatever problem there is in the error term. Let me do so essentially GLS involves estimating a transform model that overcomes, for us, autocorrelation, serial correlation, same thing, or heteroscedasticity. So it involves that. So let me give an example of heteroscedasticity. It's not what we really are focusing on in this chapter, but I think it's a good way to see how GLS works, what we mean by finding a transformation of the model. So suppose I have a very simple model. Yt equals beta 0 plus beta 1 xt plus ut. These could be i's too. This could be time series or cross section. It really doesn't matter. Where the variance of ut, sigma squared ut, is equal to sigma squared xt to the alpha, where maybe alpha is greater than 1. So what this means is that the variance gets bigger as x gets bigger. Maybe what you're doing is you're estimating sales on advertising. You want to know how much advertising affects sales. Well, the variability in sales for a little tiny grocery store in town is going to be much, much smaller than the variability in sales for, say, Safeway or something like that. So as the size of the store gets bigger, the variance in their sales gets bigger, and it scales up by some factor based upon the size. And you could use this as, this is sales, this is advertising. You might think that bigger stores have a bigger advertising budget, so this captures size. And so your variance is this way. Well, this is heteroscedastic because the variance isn't constant over time. It changes. If these were i's, if we went back to the cross section, maybe it's easier to think about. It doesn't really make any difference. yi, xi, ui. So this is just n stores. You've got their advertising and their sales. You're running this regression. Maybe you've somehow randomized the advertising through some agreement with the stores. But you're worried because you know you've got this heteroscedasticity problem. Well, suppose I did this. Consider the model. There's actually a way to figure out exactly what this would need to be by just looking at this. It's basically the square root of the problem. So it's basically the square root of this. What if I were to divide through by yi over xt to the alpha over 2? So I'm going to take the square root of this thing. Equals beta 0 times 1 over xt to the alpha over 2 plus beta 1 times, I'm using t's again, I should be using i's since I switched, times xi over xi to the alpha over 2. Alpha is some number you know. You might think of alpha maybe as 2. So, for example, sigma squared xi squared. So it goes up fast, the variance. Plus 1 over xi alpha over 2 times ut. So if we assume that alpha was 2, all I'd have to do would, or 3, let's say it's 3, something like that. So this, all I'd have to do is go into the program and create this variable, create this variable, create this variable. That's the error term. And I could run this regression and get estimates of beta 0 and beta 1. So I would generate this as my dependent variable, generate this and generate this. You wouldn't want to have a constant in this case, though actually the way I did it, you'd get one. If alpha was 2, this would be 1. This would be your constant, and this would be your variable. But in general, like if alpha was 3, they wouldn't cancel like that, and so you wouldn't have a constant. So you would run this model without a constant, and that would give you estimates of beta 0 and beta 1. Well, why would you care? Why would you want to do that? Well, look at the variance of 1 over xi to the alpha over 2 ut. That's going to be 1 over xi to the alpha, this squared, times, this is equal to sigma squared t, this thing here, times sigma squared xi to the alpha. Those cancel, and so you get sigma squared. And so with this particular transformation of the model, you get a constant variance in the model. And so you couldn't estimate this with OLS efficiently. You could use HAC errors, but this would be another way to do it where you actually model the heteroscedasticity, and you could estimate this with OLS without any correction because you've taken care of it. Now, generally, the reason we've said just use HAC errors and we didn't really go through these techniques is because you just usually don't know what this looks like. You just don't know. And you have to assume a model. And if you assume the model and it's wrong, say I assume this is what the heteroscedasticity looks like and I'm wrong, you're going to get a much worse outcome than if you assumed HAC errors. If this was actually the exact way these were formed, this would be the way to do it. It would be better than using HAC. We just don't know this in general. And so it's better just to use HAC than to try to model it. But if you did, you could estimate the model by this transformation, and you would get OLS would be efficient, consistent, all that. All right. So what we need to do now is we're going to look at a model, so the distributed lag model with autoregressive errors. And mostly we'll look at AR1 because the extension to ARP isn't hard. Let's take a simple example. YT is beta 0 plus beta 1 xt plus beta 2 xt minus 1 plus ut, where ut is phi1. I might sometimes call this rho because I'm used to calling it rho. Phi1 ut minus 1 plus ut bar. And again, this is IID, which is what we want. This is serially correlated. So if we estimate this, we might have a problem. And in fact, we do. So if I estimate this with OLS, with no HAC errors, the beta hats will be inconsistent. Sorry, that's important. They'll be consistent. So that's not what the problem is. But the estimated standard deviation or the variances, whichever, of the beta hats will be biased. And that leads to biased test statistics. So with strict exogeneity, our only choice is to, with ordinary exogeneity, our only choice is to estimate with OLS and then use HAC errors in order to get rid of the bias in the standard error. So that's one way to take care of it. But we have strict exogeneity like we do here. A better way to take care of it's going to be with this GLS technique, to find a transformation that takes care of it. And so we're going to try to get rid of the serial correlation problem, which is causing the bias in the test statistics and bias in the standard errors, through a transformation. And I think that will be a good place to stop. And then I will pick this up again next time right here. So see you soon.